All right, class, welcome to section 1.5. It's called higher order derivatives. So what does that mean? Well, since the derivative of a function is a function itself, we can go on and take its derivative. So let's say, for example, that we have some kind of a function we've been dealing with, something super easy. 2x cubed minus 3x squared plus 7x minus 1, yes? Now, what can we do? We can find its derivative. What's the derivative of this function? According to all the rules we've been learning, right? 2 times the 3 that comes down, that's a 6x squared minus 3 times 2, that's a 6x to the power of 1, right? Plus the derivative of 7x is 7, and then the derivative of negative 1 is 0. Now, if we were to look at this, this is a function itself. Whether it's a derivative of something or not, I could have started you very well with this function and said, hey, can you take its derivative? Sure. Now, this being already the derivative of f of x, what should be the notation for this? Definitely, it should be the derivative of this derivative function. We don't want to keep writing so many primes. So what we're going to do is just put 2 primes next to f of x, okay, or next to f, I should say. So that simply means now I'm finding the second derivative of this function. So what's going to be the second derivative of this? Well, 6 times 2 is 12x minus 6. Can we move on and take another derivative? Sure enough. The third derivative, yes, is just going to be 12. And then can I take the derivative of this? Sure enough, I need a notation for that as well, and so on and so on. So just as I said, you can keep taking derivatives. We can move on, by the way. What's going to be the fourth derivative of this? Well, it's going to be a 0 because it's a constant, yes? Will these derivatives change after that? The answer is no, right? After this point, they all are going to be 0, yes? Okay, so the second derivative, let's recap. The second derivative of some kind of function f of x is the derivative of its derivative. Using prime notation, we are simply going to use 2 primes, right? Rather than put parentheses and parentheses. Or we're just going to read this as double prime, yes? Now in Leibniz notation, what does that look like? We're just simply going to write, instead of, basically this is what I have. d of dx of f of x, yes, is the first derivative. Now what do we want to do? We want to take the derivative of this as well. So this is why we're going to write this as a d squared over dx squared of f, okay? And so that means, again, the second derivative. And we can move on and on. So basically, we're going to take the derivative. What this simply means, one more time, is the second derivative of f of x with respect to x twice. So both time the derivative is with respect to x. The reason why I'm bringing this up is because in chapter 4 we're going to learn about functions that have multiple variables, so multivariable functions. And so then it will matter whether we take the derivative with respect to x or y or z, whatever many variables that function's made up of. Okay, so that's going to be important later. Okay. Right, can we continue this process? Sure enough, right? Higher order derivative. So we can definitely take a third derivative. We have the second already. Now what will be the notation for a third derivative? I already wrote it up above. So we're going to use 3 primes, right? So it's the derivative of the second derivative, yes? So we keep going. In Leibniz notation, there will be the 3 over dx3 of f of x, or again, if we're calling it a y, it's the third derivative of y with respect to x 3 times, yes. Can we move on? Sure enough, we can take the fourth derivative. Now, the thing is, I did write 4 primes up here, but it just starts getting crazy. Just imagine the 10th derivative. Your eyes are going to cross if you're going to try and read how many primes are on top of f. So really, what's actually happening after this is that we're going to just start putting numbers. So that's the fourth derivative, not to be confused with f to the power of 4. This is why we're putting it in a parentheses. Also, many times we're using Roman numerals for that. But again, just to simplify things, we could just use Arabic numbers. So, but that's also why Leibniz notation was so good to begin with, because he was using numbers from the beginning. The first, the second, the third, right? And there's the fourth, right? So on and so on. We can go on. I'm not going to go through every single number out there, but the nth derivative, you can go on forever. We'll simply be writing this, whether it's a 5 or a 10 or whatever it is, the nth derivatives notation will simply be this, okay? And you can move on and on and on. So just as we went through right here, as you see, after some point, so I might as well, now that I've given it away, use the proper notation. After that, any other derivative after this is, they're all going to be 0, right? Because they're constants from here on out. Okay? So definitely we're going to put higher order derivatives to good use. So for now, let's just see. Let's just practice. So here's a function, and I'm asking you to find what? Clearly the second, because I can count 2 primes there, second derivative. Now, can I go from the function itself straight to the second derivative? The answer is no, right? What do we have to do first? We first have to find the first derivative. So even if you want to find the hundreds, unfortunately, you have to go one by one, unless many derivatives develop some sort of a pattern. Many functions develop some, sort of a pattern in their derivatives. So it's going to be easy to find them. So, okay. So again, the hundreds derivative rather than go through the first 99 first. Okay. So the first derivative, that's easy, right? We've been practicing on this. So 3 times 4 is 12. X to the third minus 2 times 2 is 4x plus 5. Okay. What's the second derivative? Well, 12 times 3 is 36, x squared minus 4. Now, did I say to go on? No. So you're going to stop right here. Many students will make the mistake to just keep on going. This is also why notation is so important, right? A function does not equal to its derivative. So you don't keep saying equal, equal, and then you lose track of what it is you're doing. Plus, you never even wrote, ever, the derivatives, yes? So it's important to stop. Put the first derivative notation, you're done. Put the second derivative notation so I know who's who. Okay, so you need to write these things down. Okay, all right. This one should be pretty easy as well. I'm asking you for the second derivative. So 2/3 times 6, that should be a 4. X to the 1 less than 6 is 5. Plus 2.5 times 4 is 10, x to the third plus 1. All right, then again, I hope you pausing me right now and finding these derivatives yourselves. Okay, so that's going to be a 20, x to the fourth plus 30, x squared, and then just comparing your answers to mine. Okay. Now, this time, pay attention. There's 3 primes here, so clearly I'm asking for the third derivative. So stop when you got to the third derivative. Okay, well, let's start at the first one. So 3 times 8 is 24, x to the 7th. The second derivative is 24 times 7. Let's see, do I have that? Is 168, x to the 6. Then I wanted one more. The third derivative is 168 times 6 is 1008, x to the 5th. Okay. Now, if I'd say keep on going and take the fourth derivative and so on, could you do that? Sure enough, right? From here it's super easy. Okay. Ooh, what am I asking you here? First of all, so I'm asking you for the second derivative, so I'm counting 2 primes there, the second derivative, and then what? Evaluate it at 1. So find the second derivative, then plug in 1, right? Okay. Now, before I find any derivatives, what should I be doing here? I have a fraction, right, with x's on the bottom. We definitely should be fixing this. In other words, bring the x to the top to have a negative exponent, right? So I'm still on my function. Yes, I have not found any derivatives yet. Okay. But I had to rewrite it in order to use the power rule. So now let's find the derivative. So 2 times negative 4 is negative 8. X, to be careful, 1 less than negative 4 is down to negative 5 plus 3. Now, I have a question for you. Should we fix this negative exponent and make it positive? The answer is no. Why? Because you have to continue, right? You have to take the derivative of this function again. So if you fix the x's, you'll have to unfix them right back so you can keep on going and taking that second derivative or the derivative of this function. So what you're doing is you're only fixing the ultimate answer exponents, right? So that's when we're going to deal with that. So what's the second derivative? Well, negative 8 times negative 5 is a positive 40. X to the 1 less than negative 5 is negative 6. And the 3 goes away, okay? And I might not even need to fix it. Why not? Because I'm not done yet. What else do I have to do? I have to plug in the 1, yes? So now let me plug in the 1. I stay with the reds for the second derivative. So 40 times 1 to the negative 6, which is 1 over 1 to the 6. That's a 1 regardless. So the answer is 40. Okay. All right. Let me just box all the answers. There you go. Okay. Same thing here. What am I going to have to find? I'm going to have to find the how manyth derivative? Well, the third one, right? I have to find the third derivative and then do what? Then plug in 64. All right, no problem. Before I even find any derivatives, what else do I have to do? I have to fix this function. So rewrite these in terms of exponents so that we can take or use that power rule. So square root is a 1/2 exponent. A cube root of x is a 1/3 exponent. Okay. So let's get on to the first derivative. The 1/2 is going to come up front. X to the negative 1/2, right? 1 less than a half. Plus 6 times a third is a 2. X to the 1 less than 1/3 is negative 2/3. All right, don't fix it because you got a lot more work to do. What's the second derivative? A half times negative 1/2 is negative 1/4. X to the negative 1/2 minus 1 more is negative 3/2. 2 times negative 2/3 is in fact a negative 4/3. X to the negative 2/3 minus 1 more is negative 5/3. Remember 1 is 3/3, so all right. And now find the third derivative. I'm going to go down here. Negative 1/4 times negative 3/2. Negative times a negative is a positive 3/8. Yes? Well, fractions are to be multiplied straight across. Negative 4/3 times negative 5/3 is, oops, I forgot about the x's. X to the 1 less than negative 3/2 is negative 5/2. Negative 4/3 times negative 5/3 is a positive 20/9. And again, you can very welcome to use your calculators. 1 less than negative 5/3, so negative 5/3 minus 1 more is negative 8/3. Okay, so now finally I have to plug in 64 into this, and you're welcome to again put in your calculator. Again, a negative 5/2 exponents really means this. I don't know if I have the room for this, but it really means that you take this 64 and put it on the bottom because of the negative exponent. The half means it's a square root, and then to the power of 5. So these are going to be really big numbers. I put them in my calculator. But, and again, it's not the point to do all this in your head. It's pretty difficult because the answer is 0.4 zeros and then a 45. So, yeah. Okay. And again, put in a calculator, not a big deal whatsoever. Okay. All right, same thing here. Find the third derivative of this function and then evaluate it at 5. Another notation, by the way, and it might be in your textbook, the third derivative with respect to x of f of x, then you will see this, x equals to 5. So again, what this means is that you're going to find the third derivative with respect to x of this function f of x, yes, and then you're going to plug in or evaluate it at x equals to 5. That thing means an at. Okay. So, looking at this function, what do you see? I see that it's a product, and I'm going to have to use the product rule, except for I'm in no mood whatsoever to do so. Why? Because I can easily just distribute this, okay, and avoid the product. Just imagine the product rule used 3 times. This is going to get insane because you have now 2 products, right? F prime times g plus f times g prime, right? First derivative times the second plus, leave the first alone, times the derivative of the second. Now you have 2 products, yes? Now take the derivative again, it's going to be twice the product rule. And again, and it's just going to get insane. So definitely it doesn't take that long. Distribute all this. Combine like terms, and I'm doing this already in my head. Minus 2x minus 7x plus 1, I hope. So 6x to the third minus 3x squared plus 10x squared, that's 7x squared. Then plus 10, minus 5x, and then minus 2x is going to get me the negative 7x, and at the end, negative 1 times negative 1 should be a positive 1. I just wanted to save some space, but you're welcome to write the whole thing out. Okay, so I need to get to the third derivative. I'll come to the first one first. So that's an 18x squared plus 14x minus 7. Oops, yeah, that's the first derivative. I was using blue for the first derivative. I'm like, something's not adding up. Okay. It's not so good about being color-coded here. I'm going to fix my mistake and write over. And make the first derivative blue. Now, the second derivative. I'm like, wait a minute. The second derivative is a 36x plus 14. See how much easier it is to take derivatives of sums and differences? You just go term by term. The third derivative is just 36, right? So sure enough, whatever it is you're plugging into the third derivative doesn't matter because that's a constant. Yes. Whoops. And that constant says that that third derivative is constantly 36 no matter what. All right. So let's try one more. I have one more example here for you before we do some applications. And I purposely picked this one because it's not pretty. So what do you see? I'm just simply asking you to find the second derivative, but this is a quotient, and we've dealt with it in the last section. So there's no avoiding the quotient rule for this one. Okay, so let's find the derivative of it. So remember, it's the derivative of the top, which is 1, times the bottom, minus, keep the top as it is, times the derivative of the bottom, all over the bottom squared. Okay, so that's an x plus 1 minus x plus 1 over x plus 1 quantity squared, which is going to be a 2 over x plus 1 quantity squared. Okay, the thing is, we in the next section will learn what to do when there's a polynomial and then a square to it, but you don't know yet how to deal with that. So in other words, we call this the chain rule. It's a composition of two functions. So if you're going to want to take the derivative of this again, what we're going to have to do is, again, we can come back to this in the next section. It will be much easier once we know about the chain rule. Okay, that's what 1.6 will be about. But for now, because we know what to do with an x squared, but we don't know what to do with the whole parentheses of things being squared, right? That's what I'm talking about, having to deal with a composition of two functions. So now that I wrote it out, I can find the second derivative. So also see how important it was that we actually didn't leave it like this, but we simplified it, because I much rather deal with this than to this initial mess here. Okay, so the second derivative is the derivative of the top. The top is a constant, so that's going to be a 0 times the bottom, minus, leave the top alone, times the derivative of the bottom, which is a 2x plus 2, all over the bottom squared. So this goes to 0. That's a negative 4x minus 4 over x squared plus 2x plus 1 quantity squared. Now, this is perfectly fine. In fact, oops, not squared. Yeah, it's squared. In fact, this quotient can be simplified some more. It does, believe it or not, have common factors. This is totally fine for our purposes of checking if you know how to use the quotient rule, right? What does it mean to find a second derivative? But I'm just going to simplify it for those of you who would like to have the most simple answer. So fractions are to be reduced, right? If they're common factors, you need to reduce them out. So can I factor the top? Sure enough, I can factor out the negative 4. Can I factor the bottom? Yes. Remember, where did the x squared plus 2x plus 1 come from? It came from an x plus 1 quantity squared, yes? Now when I square that again, what do I do with these two 2's? I'm going to multiply them and make a 4 out of it. So I don't have much room, but there it is. So this is what I'm saying, that there was a common factor. What's the common factor? An x plus 1. So the answer is going to be a negative 4 over x plus 1 to the third power. Okay, all right. So we're going to stop this video here and just continue. We're almost done. Just a few applications, okay, for second derivatives.